Okay, and welcome to the University of Lethbridge. Our university's Blackfoot name is Iniskim, meaning Sacred Buffalo Stone. The university is located in traditional Blackfoot Confederacy territory. We honor the Blackfoot people and their traditional ways of knowing and caring for this land, as well as all Indigenous peoples who have helped shape and continue to strengthen our university community. Today at the Lethbridge Number Theory and Combinatorics Seminar, we're very pleased to have the postdoctoral fellow Mathieu Dutour from University of Alberta. Mathieu will speak about Theta-finite pro-Hermitian vector bundles from loop groups elements. Mathieu, is it okay if we video your talk?
Yes.
Great, thank you. Well, please go ahead.
Okay. Well, thank you for the introduction and also for inviting me to speak at this seminar. So today I want to present a project that I have joined with Manish Patnaik at the University of Alberta on some relations between the theory of loop groups and hierarchical geometry. Now, I will say just a few words about those domains without going into too much detail. So the construction of loop groups that I'm going to use was performed by Howard Garland, and it was an adaptation of the construction of Chevalier groups and lattices to the case of a particular affine Katsumi algebra. Now, hierarchical geometry is a bit complicated to sum up in a few words. Roughly speaking, you want to study objects coming from algebraic geometry, let's say over spec OK, where K is a number field, and you want to put metrics at infinite places. The part of hierarchical geometry that I will use in this talk is related to some work by Jean-Benoit Bost on pro-Hermitian vector bundles and their relation with theta invariants. And this work was further continued by Bost and François Charles. Okay, so there's a lot of material to unpack before we can get to the core of this project. So let's just dive in with a few facts about the finite dimensional case. Okay, so a Lie group is just a group which is also a manifold. The two group operations have to be smooth maps. For instance, you have the linear groups and the projective linear groups. Now, when you start studying Lie groups, you see a construction that from a Lie group you can build something called a Lie algebra. It can be identified to the tangent space at identity, but there are some details that I won't mention here. And you can compare those two notions using the exponential map, which gives you a way to identify a neighborhood of 0 in the Lie algebra and the neighborhood of 1 in the group. Okay. But there is an independent definition of the algebras. There are finite dimensional vector spaces endowed with brackets. For instance, the space of matrices. And of course, a morphism of the algebras is just a linear map that respects this bracket. So we know that from a Lie group, we can go to a Lie algebra, but can we go in the other direction? Can we build a Lie group from a Lie algebra? So to do that, we have to talk about representations of the algebras, which are given by morphism from the Lie algebra G to an algebra of endomorphisms. The first, I guess, non-trivial example is the adjoint representation given by this bracket. And there's a particular case that I want to mention, which is when the Lie algebra is a trivial center. In that case, this add morphism is injective. So you can really embed the Lie algebra into an algebra of endomorphisms. Okay, so using that, now I can state at least a very, very particular case of the correspondence result, Lie's third theorem. So here, a very particular case, every simple Lie algebra is the Lie algebra of a Lie group. So for a simple Lie algebra, the center is trivial. So you can embed G into an algebra endomorphism, and you can take the exponential of those endomorphisms that generates a group, which is what you want. Okay, so what should you remember from this section? The process that we just saw was we start with a Lie algebra, we find a representation, we take the exponentials, and we get the group. So that's the basic process here in the finite dimensional case, but now we are going to go infinite dimensional.
Simple?
Simple, it's non-abelian with no non-trivial proper ideals. I think a bit non-abelian is built into the definition. Okay, so now let's study infinite dimensional algebras. So we start with a finite dimensional Lie algebra, simple, so that's the definition that I just gave, and split, so it has a Cartan algebra. So we start with that, and we twist that algebra by the formal Laurent series. I'll say what those are just after. With this tensor product, you obtain something that's infinite dimensional over R. So you don't say that it's a Lie algebra, it's a Kac-Moody algebra. It just means infinite dimension. And the bracket on that tensor product is defined on simple elements, component by component. So just to make it clear, those formal Laurent series have finitely many terms in the negative direction, infinitely many terms in the positive direction. So here, there's a lack of symmetry that's very important when you study loop groups between the positive and the negative side. Actually, the work that Garland did is a lot subtler, but I don't want to make this talk even more technical, so I'll just conveniently sweep under the rug everything related to completions. Okay, so that's not the only way to get those group algebras. You can also do something that's maybe a bit more closely related to the finite dimensional case with Cartan matrices. And what you get through this other process is not actually quite this algebra, but the central extension. So the central extension of the Kac-Moody algebra by the algebra A is a larger algebra in the center, which contains A in its center. So we have an exact sequence, and we have actually a particular type of such central extensions, which are called universal. Now here it's the technical definition, but what we'll use is actually only the results that Garland proved. So for this loop algebra, G tilde, that we saw in the previous slide, there is a unique universal central algebra, a central extension, which as a vector space is obtained by a direct sum with a one-dimensional algebra, but the bracket is a bit more complicated than just taking a direct sum of brackets. And this element C that we had to add is a central element. So if you look at this formula, if you don't consider loop elements, you get 0 using this formula. But if you take the bracket of two loop elements, so with alpha and beta equals 0, you still get a result that has a component according to C. So in particular, even though we have this direct sum, the inclusion of G tilde into G hat is not a morphism of the algebras because it's not compatible with those brackets. Okay. Now, this isn't actually quite enough, because the problem is that if you look at G tilde, the loop algebra, or G hat, the central extension, you don't have a particularly good notion of roots. The problem being that, for instance, one of the problems being that the root spaces are infinite dimensional, which is not really great. So to correct that problem, we are going to do one more extension. So we introduce a derivation of G hat called the degree operator, which, as you can see on this formula, it doesn't care about the central component. It doesn't see alpha. It only cares about the loop part, this x tends to t to the n, and on those elements, it multiplies by the degree, hence the name. Now, whenever you have a derivation on the algebra, you can always do a construction which is called a semi-direct sum. So a semi-direct sum is a bit like a semi-direct product of groups. You have, as sets, you have a direct product with a twisted group law. Here, you have a direct sum as vector spaces with a twisted bracket. So it's a bit similar, but here with the algebras. So this construction here will be very useful to talk about the roots, this time of this extended loop algebra. So let's do that now. So because the Lie algebra is split, we can take a Cartan subalgebra H. And now we can define the extended Cartan algebra by adding those two extensions, C and D, to it. So now let's take a system of simple roots of the classical Lie algebra G, which was finite dimensional, alpha 1, alpha n. Alpha 0 is the highest root. Now, because those alpha i's are linear forms on H, we can extend them trivially over C and D, and that gives us linear forms on H hat E. Okay, so in that way, we extend those roots, and we have to define, and of course, the highest root being a combination, a linear combination of those alpha i's, is also trivial at C and D. Now we have to define one more thing, which is called the imaginary root, iota, which has a linear form on H hat E, doesn't care about the loop part in H, doesn't care about the central part, so this alpha C, it only sees this last coefficient lambda. So that's one more linear form, and with it and the highest root, we can build the L plus 1 root alpha L plus 1. Now, because we've done that, we can take that new root and add it to the L others, and in that way, we get a system of simple roots, this time of the extended algebra. And we can also describe every root of the extended algebra. They are of two different types. Either you can write them as a classical root plus n times this imaginary root, or it's just a multiple of this iota. Just like in the finite dimensional case, we can say a lot more things about the root spaces. This time they are finite dimensional. If the root is of this first type, which is called a Weil root or real root, the root space is one-dimensional, just like in the finite dimensional case. If it is of the second type, the dimension is L, the dimension of the Cartan algebra. So it's a larger dimension than in the finite dimensional case. But those are all the affine roots, and we know exactly the dimensions. Okay, so if you remember the end of the first section, where I gave you the process that we had to follow, we start with the Lie algebra. We have our Lie algebra now. Now we have to find a representation. And to do that, we need one more construction on the algebras, which is the universal enveloping algebra. So you take the sum of the tensor powers, and you take this quotient, where you identify this sort of commutator x tensor y minus y tensor x to the bracket. And that gives you this universal enveloping algebra. And you can do similar constructions for subalgebras of that. For instance, a parabolic algebra, P hat E, or these triangular subalgebras. Okay. And using that, we can define the highest weight representations. So we start with a linear form on H hat E, which has some hypotheses that I won't get into the detail of. And we also take a non-zero vector V0. We can define an action of this P hat E on this single vector by saying if you're in the upper triangular, well, you act by 0 on this vector. But if you're in the Cartan algebra, you act by this lambda, by this linear form lambda. So with that, we get an action of P hat E on this vector, or on the space it generates. And that, having an action of P hat E, is the same as having a structure of a U P hat E module. So because this RV0 is a U P hat E module, we can take the tensor product of this above this U P hat E with the full universal enveloping algebra, and that in a way that completes this action into an action of the entire G hat E. And we just take a quotient of that by a well-chosen submodule. Now that gives us something called the highest weight representation associated with lambda. It's infinite. It's an infinite rank representation. Okay. So now we have this representation. We can describe the weights, which are those linear forms on H hat E such that this
sort of generalized eigenspace is non-zero. But now those weights have a very, very particular structure. They can all be written as this lambda that we fixed minus an integral positive linear combination of those roots. So if you order the weights according to their depth, the sum of those coefficients, you find a nice picture, which is that they all fit inside a paraboloid, with lambda being the sole weight at the top. Now here, a parabola, for instance, in the SL2 case. And so with this picture, you can see why it's called a highest weight representation. Lambda is the highest weight. Now, because this degree operator D was an element of H hat E, we know its action on every weight space by definition of the weight spaces. It acts by taking the image of D by this weight mu. Now, if you look at the way we can write this mu, and if you remember that alpha 1 up until alpha L are trivial on D, you'll see that this mu of D cannot see M1 up until ML. It can only detect ML plus 1 because this last root that we had to add was the only one that could see this degree operator. And so this last integer in this decomposition plays a special role, and we call it the level of the weight. Right, so now that's the second step of the process. We have the representation. Now we need to take exponentials. So in the finite dimensional case, that wasn't a problem because we can always take the exponential endomorphism. But here, infinite dimensional case. So we have to say something about why that works. So the first type of elements are going to be those psi A's. So those are elements in the extended algebra, which are defined by taking those E alphas, which are elements in the classical root space of a finite dimensional algebra, tensor a monomial, and corresponds to a real root. Now that is an element of the extended algebra, so it acts on this highest weight representation. Can we take the exponential? Yes, because the action is locally nilpotent. So when you apply to any vector, the exponential series is finite. So it makes sense to take the exponential of a multiple of that. But that's not quite enough, because here we only take into account monomials. We want to take into account formal law series, which can have infinitely many terms. And so here there's one more thing to say, which is, well, why can we take infinite products of those exponentials? Why does that make sense? So if you take any formal law series, you can consider this infinite product, because when you apply it to any vector, so you have an infinite product applied to a single vector, infinitely many of the factors are going to act as identity on that given vector. So for any vector, the product makes sense. It doesn't mean that as an automorphism, this infinite product is finite. It just means that when you apply to any vector, it's the same as a finite product applied to that same vector. And those automorphisms generate the group, which is the loop group, G hat, which is called the loop. Okay. Now here, with those elements, psi A's, and with those automorphisms, chi alphas, we only really took care of the loop part of the algebra and the central part, the exponentials of those endomorphisms. We didn't take into account the degree operator, this last extension. So for that, we have to define one more automorphism, which is essentially the exponential of the action of that degree operator. Now, if you remember, I described the action of the degree operator on any weight space. So taking the exponential of that action was just here taking tau to the power that action for on any weight space where the level is n. This automorphism behaves very well with respect to those generators of the loop groups, because if you take a conjugation, what you find on the right-hand side is the same generator with the parameter multiplied by this real number. It's often called a rotation of the loop parameter. And using that, we can take a semi-direct product of groups with R plus star. So that's the extended loop group, but it's a bit too large for for this project, we often just consider a slice, a subset of that giant group. So it's just a subset, this g hat theta of tau, just a subset, not a subgroup, for a fixed real number. Okay. So, if you remember now the few words that I said about hierarchy of geometry, I said that some of the objects had to be considered above spec OK, where K is a number field, and some of those objects were Hermitian vector bundles. In this talk, we will only consider the simplest of all number fields, which is Q. So an element of a spec Z, a Hermitian vector bundle of a spec Z, that's the same as a lattice with a metric. So now what we're going to do in this section is define a metric and a relevant lattice. Okay, so here, with this statement, the algebra UG hat E is generated by the psi A's. Here, it's actually a bit subtler than that because of those things about completions. But here, let's just say that it is actually generated by those elements. So you can define an involution on this algebra just by specifying how it acts on every of those elements psi A's and how it acts on tensor products. So on an element psi A, it just switches the sign of the root, and on a product, it reverses and applies itself to both factors. And with that, we can define a metric on V. The definition is a bit technical, but we'll see an example just after. Okay, so you start with two vectors in V, V1 and V2. Now, this representation was built in such a way that any vector can be obtained by this single vector V0 we started with by applying an element of this giant algebra, UG hat E. So those two vectors, V1 and V2, can be obtained from the same V0 by applying two different elements, gamma 1, gamma 2. Okay? So now you can take the vector V0, apply gamma 1, and then apply this gamma 2 star to it. What you get is a vector in V, and you can project that onto this single weight space that's at the top, associated with the weight lambda, and that highest weight space is one-dimensional. So when you take this projection, what you get is a coefficient, and that coefficient gives you your metric. Now, of course, you have to prove a lot of things to say that this is actually a metric, actually in a product. Garland does that. Okay, so let's see an example right now. So imagine that you want to compute the norm square of psi minus A V0. So you take V0, it's at the top of the parabola, the weight space at the top. You apply psi minus A, you get in the parabola, assuming lambda minus A is a weight, but that's something we can do. So you apply psi minus A, you get in the parabola. Now you apply psi minus A star, which is psi A. Well, you re-add A, you get back up to that top weight space. So this psi minus A star, psi minus A V0 is just in this highest weight space. And so it is a coefficient times V0. That coefficient is the square of the norm. Okay. So that's the metric. So that's the metric, and as I said, we also need a lattice. So again, to define this lattice, we have to go back to the universal enveloping algebra. And so here, what we have to do is talk about Chauvet basis. Now, a Chauvet basis of that algebra is a basis such that if you take the bracket of two elements, it gives you an integral linear combination of the elements in the basis. Okay, so it's a very particular type of basis. But what Garland proved was that there exists such a basis here in this case. And if you denote by UZ the Z span of this basis, which is stable by the bracket by definition of a Chauvet basis. So if you denote by UZ the Z span of that basis, and you apply all of those elements to V0, what you get is a lattice VZ included in V. And you can also do, you can also choose this basis in a way that each of the elements, when applied to V0, gives you a vector in a single weight space. Now, this lattice is not just, I mean, we could have found many lattices, including V. So why did we have to do that? Well, the reason is that it's very particular because the metric, when you restrict the metric, is it okay? Oh. Okay. So it's a very particular lattice because when you restrict the metric to it, it takes integral values. So it's not just any lattice, it's one that's closely connected to the metric. Now, because we can choose the Chevalier basis in a way that those vectors can be, those elements applied to V0 land in weight spaces, we can define sublattices of every weight space, just by taking this intersection. And we can regroup those sublattices according to their level. So you have WZN, you have VZN, which is everything of level at least n plus 1, and WZN, which is everything of level exactly n. Now there's an observation that we can make, which is if you take the full lattice and you quotient by everything of level at least n plus 1, what you end up with is everything of level at most n. That's what remains. And this identification is compatible with the metrics. So on the right-hand side, you have the restriction of the metric on Z, on V. On the left, you have the quotient metric. Now, is everyone okay with quotient metrics? So, yeah, okay. Right, so if we were to work in the finite dimensional case, preserving a lattice, that would give you a discrete subgroup, essentially. Here, it's not a discrete subgroup, but it's a good analog of what should be a discrete subgroup. Same if you preserve the metric, you're not compact here, but it's what it should look like. And now, two more technical definitions. Those two groups, B plus, B minus. Now, rather than giving you the precise definition, I prefer to give you more of an idea of what they are. If you remember that picture with the parabola and the weight spaces which are all located inside the parabola, an element of B minus will push those weight spaces downward. So you apply an element of B minus to an element of a weight space, you get a multiple of the same vector and things of depth that are greater. B plus pushes upward. Multiple of the same vector plus things of lower depth. Okay? Right. Now we can come to the hierarchy of geometry side of this project, which is a very quick summary of Bost's work, Bost and Shaw. Okay, so as I said before, if you consider a Hermitian vector bundle on spec Z, you can say that it's the same as a Euclidean lattice, so a lattice with a metric. For those objects, you can define something called the theta invariant, which is the logarithm of this special value of the theta function. So this sum of exponential minus pi norm square of v. You can also define the dual of that lattice, and you can relate the theta invariance by the Riemann-Roch formula. So the difference of those theta invariants is the arithmetic degree of E, which is minus the logarithm of the coordinate. So you have a relation here between theta invariants. And now, because we work mostly with infinite dimensional representations, we want to generalize those to an infinite dimensional setting. So that's something that Bost did. The easiest generalization is called an Hermitian vector bundle. So you start with an inductive system, so a collection of lattices with inclusions, everything being compatible with the metrics on those lattices. If you take the inductive limit of that thing, you can put a norm on it, and it gives you something called an Hermitian vector bundle, because it comes from an inductive system. Also in the Euclidean lattice. Now, for those objects, you can generalize the theta invariant because this inductive limit here in this case, it is always countable. So what you can do for the theta invariance, what you can do is either copy the definition, this sum of those exponentials. You can also take the limits of the theta invariance of the finite things in the system. That may be infinity, but at least it's well defined. It doesn't depend on the inductive system that gives you your object. So it's a pretty nice invariant. The problem arises when you consider pro-Hermitian vector bundles. So things coming from projective systems. So projective systems are this time a collection with surjective maps and an isometry between En mod the kernel and the lattice before that. Now the projective limit of such a system can be endowed, well, not quite a norm, but a semi-norm. So a semi-norm is, at least here in this talk, a norm that can be infinite. So you can put that, and the result is a pro-Hermitian vector bundle. The problem being here that the projective limit, here this projective limit, is not necessarily countable. So what do you do if you want to generalize the theta invariance to that? Well, because it's uncountable, you can't really take the sum of those exponentials, because the set, even the set, is much too large for that. You could say, well, we could always define by the limit, because that was the other possibility. The problem here is that any given projective pro-Hermitian vector bundle could come from many different projective systems. And those limits don't have to agree. So if you try to define an invariant of the pro-Hermitian vector bundle by taking those limits, you end up with a problem. So here, one of the points of Boss's work, recent work, was to find a way to make this generalization. Now what it does is a lot more complicated than what I present here. But essentially, if you restrict yourself to projective systems which satisfy one more hypothesis, this strong summability condition, if you restrict yourself to only those projective systems, then the limits do agree. And it gives you actually the right invariant. So he does that in a way that's, again, a lot more intricate than just saying that. But for a special class of projective systems, you get the right thing by taking those limits. Okay. Now, I mentioned in the title of the talk, Theta-finite. Now, if you look at this condition, here, again, it just has to be satisfied for one epsilon. Having it for one epsilon is enough to give you the invariance. But if you have the same condition for every epsilon, positive, then what you get is what's called a theta-finite pro-Hermitian vector bundle, because now you can define the theta function of it. Okay, and I would also like to mention that in his work, Boss studies a very particular case. He finds examples of such theta-finite pro-Hermitian vector bundles, and he obtains them by taking the L2 sections of a finite rank Hermitian vector bundle on a complicated object that he calls a smooth formal analytic surface. Now, it was kind of reasonable maybe to expect that those would be most of the examples that we could find, if not the only examples. Oh yes, to prove that those are theta-finite, he needs a hypothesis that I'll mention again later. So now, finally, before I can talk about the project, so we have those two notions, Hermitian, pro-Hermitian. They have a relation between one and the other, which is by duality. If you take an inductive system, the dual is a projective system, and vice versa. So you have those theta invariants, and in the finite dimensional case, you could relate them. Here, if you assume that everything is defined, can you relate those two invariants? The answer is no, not in general. So I'll mention that again later, because that may be a direction for future work. And finally, I can now talk about the project with Manish Patnaik. So here in this project, we have those two areas which seem very different, loop groups and hierarchy of geometry. How can we build an example of a pro-Hermitian vector bundle from an element in a loop group? So we start with an element in this slice of the extended loop group, an element G and this eta of tau, and we use that element to twist the metric that we saw before. And now we can build a projective system, which is by taking those successive quotients. So you take, again, Vz, that's the entire lattice. Vzn is everything of level at least n plus 1. So you take those successive quotients with the projections, those Qn's are the projections. And if we make two assumptions, so G, the element in the group, has to be in this B minus, which pushes the weight spaces downward. And this real number tau has to be smaller than 1. If we make those two hypotheses, then we can prove that the projective system satisfies the strong solidity condition for any epsilon. And so the H0 theta invariant is well defined, and we have a theta-finite example. Okay, so now maybe the question that could be asking yourselves, why do we care about that? Why is it a relevant example? So the thing is, in Boss's work, there's this hypothesis which he calls pseudo-concavity, and he uses that to study his examples. And it is the same hypothesis as this tau smaller than 1. So what we could ask ourselves is the example that we're finding one of his examples? Or is it something fundamentally new? So if we imagine for a moment that the example that Patnaik and I found was the same, was one of his examples, then it would come from a finite rank Hermitian vector bundle. And if we went through the same constructions that he did, what we would find was that the dimensions in this projective system would grow linearly in n. And actually, in our case, we find that it doesn't grow linearly. It grows as exponential square root of n. So it doesn't seem likely that the example that we're finding is one of the examples that he studied. And even if we imagined a generalization of this theory not on formal analytic surfaces, but formal analytic higher varieties, then the growth of dimension would be in the power of n. And so it's still a new example because exponential square root of n grows much larger, much more quickly than any power.
Why did you say likely? Why you said likely?
Yes. So why do I say likely? Because here it's a bit of an intricate argument that I use, because what I say is if it came from a finite rank vector bundle, then most likely his construction would give the same as our construction. But it's essentially if I feel like the only way we could make that precise would be to prove that it came from a finite rank vector bundle. So saying it doesn't come from a finite rank vector bundle because if it did, we would get that, but we can't prove that we get that. It's let's just say that his construction would have to be compatible with the notion of level, because the way he defines his projective system is by considering the sections of the finite rank bundle restricted to a thickening of a curve of order n. And essentially here, this notion of thickenings would be controlled, would be very much compatible with the level. So it seems that the only projective system compatible with the level that we could find would be this one. Maybe with a different metric, but it wouldn't change the fact that the dimensions here grow too quickly. So that's why I say likely, because I can't prove it for sure, but it seems like a different example. Okay. So let's just go through a few elements of the proof. Now, I made this observation a bit earlier, which is that if you take the full lattice and you quotient by everything of level at least n plus 1, you get everything of level at most n. It was compatible with the matrix. But here we twisted the matrix by an element of the root group. So that, in general, makes this identification incompatible with the matrix. And the reason for that is that the element G, again, in general, has a unipotent component. And if you take a unipotent transformation, it won't preserve the orthogonality of the weight spaces. So in general, this identification is no longer compatible with the matrix. And that's actually taking care of that is the most difficult part of the proof. And that's where you have to make this hypothesis G is in B minus. Because with that hypothesis, you can find something that you can call a Hiwari-Matsumoto factorization, which makes this unipotent element, which makes you able to factor this element in a way that each part can be controlled precisely. So you can relate the norm of the unipotent applied to a vector to just the norm of the vector. So that's really the most complicated part of the proof, because once you've done that, the only elements essentially remaining in G are going to be elements which act as scalars on every weight space. And so those you can take care of much more easily. So now I'll just mention very quickly the other steps. So as I said, essentially the elements that remain once you've taken care of the unipotent component of G act as scalars on every weight space. So you can give precise estimates of the norms when you twist the metric by such elements. And what you end up doing is taking out of the norms a factor tau to the minus n. You also have to control the dimension of every lattice in the projective system. That's something I already mentioned, but I didn't say how you found those estimates. So that's based on the work of Katz and Peterson, and itself based on the Wildcat's character formula. One of the last ingredients is an estimate, a Groenewegen estimate, which relates a theta invariant to the shortest length of a non-zero vector in a lattice. And now the crucial part of the end of that proof involves the second hypothesis, tau smaller than 1, because now what you'll find in this strong summability condition, you have to prove that something is finite, that something converges. And so you have a bunch of exponentials of square root of n, minus square root of n, things like that. But you have a factor tau to the n. And tau to the n decays much more quickly than any exponential of square root of n could increase. And so that allows you, this hypothesis allows you to complete the proof and to prove this strong summability condition for any epsilon. Okay. And now just a few elements that we are thinking about for future work, either on theta invariance or on some things related to groups. So here, I've only talked about Q as a number field. Obviously, there are much larger number fields, so we should do something about that. Maybe state the same result for larger number fields, or maybe do something different. Everything should pretty much be the same. Maybe it would be a bit more complicated to write down, but it should all be pretty much the same, at least for totally real number fields. So number fields that only have embeddings in R. One thing that's that you could also find strange is that in this talk, in the finite dimensional case, I talked about the adjoint representation. But then in the infinite dimensional part, I didn't mention the adjoint representation at all. So actually, the adjoint representation, well, you could copy the construction of loop groups in that case. That's something that Garon does, and he gets something that you can call an adjoint loop group. You can also use the loop groups that we've seen in this talk in conjunction with the adjoint representation. Now, so why didn't we use that here? Because actually using the adjoint representation would be simpler. So why didn't we use it? The reason is that if you copy the same kind of projective system, you would get something that seems to be growing linearly in dimensions. At least if you exclude the first part, the term n equals 0. But it seems to be growing linearly in dimension. So the argument that I used before to say it's a new kind of example here doesn't work. Maybe it's still a new kind of example, but it's not as easy to convince yourself of that. So that's one of the reasons why we still have something to do about this adjoint representation. In the elements of the proof that I mentioned, there was this hypothesis G is in B minus, to be able to take care of those unipotent parts. But is it actually a restrictive hypothesis? So the ideal case would be to define the invariant for any element in the loop group, and this invariant would be K invariant on the left, because K preserves the matrix, so when you look at the theta series, multiply by K on the left, it doesn't change the matrix. And it would be gamma intersect B minus invariant on the right, because essentially those would preserve the projective system. So now, if for any element in G hat, we could find a representative in B minus modulo these two groups, then the hypothesis would not be restrictive, because you could always find an element modulo these two groups that would land in the right subgroup. So the reason why we think there might be something to that is there is such a result for function fields in positive characteristics. And you could copy the arguments even in characteristic 0, but for finite places. So maybe the same result is true also at infinite places. But the same argument doesn't work. So if we can find a way to prove that result, then it would make the result better. And that would actually be useful for later points that I want to make. Okay, I said earlier that the theta invariant for the ind bundle and the theta invariant for its dual, which is a pro bundle, those could not be related in general by a Riemann-Roch formula. Here, the way we can see that in this case of loop groups is that you have to have this hypothesis tau smaller than 1. This one you cannot do without. But when you take the dual of something, you tend to invert the metric, essentially. So if you start, let's say, with an in bundle, you need this tau smaller than 1 to make the thing converge. You take the dual, you get 1 over tau, which is larger than 1. And so the thing doesn't converge for the pro bundle. So essentially, when you're studying in and pro bundle in this loop group context, you essentially have to choose which one will exist, which invariant exists. And so you can't relate the two by a Riemann-Roch formula. Now it doesn't mean that because you can define those theta invariants by taking limits, at least in favorable cases, maybe you can extract a regularized version of such an equality. That maybe that would give you something that's relevant. So that's something that we are thinking about, because it would be, I think it would be very interesting to have a Riemann-Roch formula in this context. Now, in the last slide, I said that it would be interesting to see if the hypothesis G in B minus is restrictive or not. If it wasn't restrictive, maybe you could use that, the fact that the theta invariants are defined for every element of G to help define the negative loop Eisenstein series. Now, one of the things that that we are thinking about is that maybe in this negative loop case, maybe we can use theta invariants to help define those series and to study them. But in order for that to work, those theta invariants would probably have to be defined for every element of the group, not just in a particular case. And the last point that I want to make here is that in hierarchical geometry, you have this class of results which is very important, which are called arithmetic Riemann-Roch theorems. And they relate two types of construction. A construction which is called the determinant line bundle, which is essentially associated to complex geometry, and you have the Quinian metric, things like that. And on the other side, you have intersection theory. Now here, in the case of loop groups, you can find in a book by Pressy and Siegel, you can find a construction of something that they call the determinant line bundle in the loop group case. So it's not the same as the classical one, but it's still something that looks like it with a metric. On the other hand, Bost and Charles have recently defined some intersection numbers on those formanalytic surfaces, which is something that's still very closely related to what we're seeing in this project. So is there the same kind of result that links those two constructions, like those arithmetic Helmholtz theorems? So that's something that would be, I think, very complicated to study. But if we could somehow obtain that kind of relation, I think it would be very interesting. And I think I'll stop here. Thank you for your attention.